stop curating synonym lists.
RM3 expands each query using what your top results already say. By the end, you will understand how to take a short query, mine the top hits for good expansion words, and re-rank results to get more relevant hits without training a big model. I'm Professor Pi, teaching search and IR with simple Python. RM3 Pseudo-Relevance Feedback solves a common gap in search. Users type short queries. Those queries miss useful words that appear in relevant documents. RM3 fixes that by looking at the top results, assuming some are relevant, and borrowing their vocabulary to enrich the query. People reach for this when their baseline lexical model, like BM25, brings back useful but shallow matches. RM3 often improves precision at the top of the list, with little latency cost on small to medium collections. Intuitively, RM3 asks two questions. What do the top hits talk about? And which words there should we add to the query to better describe user intent? It then mixes the original query with a small weighted distribution of those feedback words. Strength: simple and effective. Weakness: if the top hits are off-topic, feedback can amplify noise. We will build a tiny pipeline that shows this idea end to end. We will start with a 3-document toy corpus, score with TF-IDF, move to BM25, measure ranking quality with NDCG, run RM3 to expand the query, and then compare the NDCG after expansion. No heavy libraries required. Now, we will create the tiny corpus and compute simple TF-IDF scores. This snippet creates a 3-document toy corpus and evaluates a simple TF-IDF score for the query terms. The list docs holds short texts, and the list D stores tokenized versions. The counter DF records how many documents contain each token, which feeds into the IDF calculation using a log with add1 in the denominator for stability. The list SC accumulates for each document the sum of term frequency times inverse document frequency over the query words phone battery life. Higher values indicate better lexical overlap weighted by rarity. The printed TF-IDF scores show which documents align with the query vocabulary and by how much. Next, we will replace raw TF-IDF with a BM25 style scorer that normalizes for document length and term saturation. This example moves from TF-IDF to BM25, which normalizes by document length and dampens term frequency. The variable Q holds query tokens, and avddl computes the average document length. The dictionary IDF uses a BM25 style formula with a +1 shift to avoid negatives. Constants K and B control saturation and length normalization. The list BM25 sums each term's BM25 contribution per document. The list order sorts document indices by decreasing BM25 score with an index tiebreaker for stability. Increasing K rewards repeated terms more. Raising B amplifies length normalization. The printed tuple shows the top-ranked document index and its BM25 score. Now we will measure how well that BM25 ranking matches known relevance labels. This snippet computes NDCG app3 to assess the BM25 ranking quality with graded labels. The dictionary rel maps document indices to gains, where higher is more relevant. The list gains picks the top K BM25 results and converts them to graded gains. And DCG sums discounted gains by position using a log base 2. The list ideal sorts known gains to form the best possible ranking, and IDCG is the reference normalization. Dividing DCG by IDCG yields NDCG in the range from 0 to 1, where higher is better. The printed value summarizes how well BM25 ordered relevant documents near the top. Next, we will mine the top hits for candidate expansion words and build the RM3 weighted query. This snippet performs RM3 pseudo-relevance feedback by mining top-ranked documents for expansion terms. The variable C counts tokens from the top K initial results, and FB selects the M most frequent terms not already in the query. The dictionary WQ builds a term weight mixture. Alpha keeps the original query probability mass, while 1 minus alpha allocates mass to feedback terms by their relative frequency. The list BM25E recomputes scores as a weighted sum of BM25 contributions, using WQ as term weights. Lower alpha trusts feedback more and can shift ranking more aggressively. Higher alpha stays closer to the original query. The printed tuple shows the new top hit after expansion. Finally, we will measure the re-ranked list to see if expansion helped. This example measures the ranking after RM3 expansion with the same NDCG at 3 protocol. The list ORD-E captures the top results under BM25E, which already includes weighted query terms from feedback. The expression DCGE recomputes discounted cumulative gain using the same graded labels in RAL. Dividing by IDCG, computed earlier from the ideal ranking, yields a normalized score that is directly comparable to the BM25 baseline. If you increase alpha, the gain may shrink because expansion matters less. Decreasing alpha can help when feedback terms are highly informative. The printed NDCG shows the RM3 re-ranking moving relevant results nearer the top. In a real project, this same flow maps directly. Use your document store instead of the toy list. Compute BM25 scores over your inverted index. Take the top few hits as feedback. Extract frequent terms. Mix with the original query using alpha, and re-rank. This is low effort and plugs into existing search stacks. Recap: RM3 pseudo-relevance feedback expands queries by mining the top results for frequent terms. Use it when short queries and lexical gaps prevent relevant documents from surfacing. Caveat: if the initial top results are off-topic, feedback can amplify errors. Next step: tune the mixing parameter alpha and the number of feedback terms to find the sweet spot for your collection. If short practical IR helps, subscribe and watch the IR videos.